Hello everyone, and welcome to another session of Computational Algebraic Geometry. Today we'll be talking about linear subspaces of affine and projective spaces. Let's get started. What we are aiming for is to construct these spaces so that there will be coordinates on these spaces, which means there will be polynomials defined on these spaces in terms of the coordinates, which will then get us closer to computational problems. In particular, what we want to do next week is to find, let's say, all lines in surfaces, all lines in a given surface in the projective 3 space. What you can do right now is to try to put coordinates on the space of lines inside of a 3 space. So that's something of a challenge. It's the first interesting case, first non-trivial case. And you can already start playing around with trying to describe a line by a pair of points. So this is a good point to stop the video if you want and play around. If not, we will start with the baby case of this problem, the space of lines inside of a plane. Let's consider the lines in the plane. A line is defined by 2 points on the plane, and we can try to parameterize the space of all lines by pairs of points on the plane. So the pairs of points will be 4-dimensional, PQ in A2 times A2. Of course, you want to remove the diagonal because P and Q, your 2 points, should not be the same if you want to define a line. So we have a 4-dimensional space here. On the other hand, you will see that each line is over-parameterized by this construction because, of course, for any pair of points lying on the same line, which there are line times line many, so a 2-dimensional space of such points, we will just recover the same line. Meaning that we have a 4-dimensional space of pairs of points on the plane and 2-dimensional subspaces, certain 2-dimensional subspaces correspond to lines. So we can expect that the space of lines should be 2-dimensional. So this kind of dimension counting argument will always work in these parameterization problems of linear subspaces. But in this case, we can do even better. There's a trick that is specific to the fact that lines are codimension 1 in the plane, meaning that a line is in fact cut out by a single equation, and a single linear equation at that. So I can describe a line with the following linear equation, where x and y are coordinate functions on the plane A2. I write ax plus by plus c equals 0. So a, b, c here are constants, and the 0 locus of this linear equation is going to describe a line. And here a, b, c are well defined up to scaling. So if I scale this triplet, I get the same line, and from a line I can recover ABC up to this multiplicative constant. Therefore, from a line, I get a point in P2, the homogeneous coordinate ABC. Conversely, every homogeneous coordinate ABC in P2 will give me a line, except for one triplet. I cannot have 0, 0, 1, because this will correspond to 0 times x, 0 times y plus 1 equals to 0. No line satisfies this equation. I just get the empty set as its 0 locus. So if I remove this single point from P2, 0, 0, 1 from P2, then I have a bijection to the space of all lines inside of the affine space A2. So on the one hand, this is very instructive, but to reap the full benefits of this example, try to take 2 points in A2 again, and then try to cook up the coordinates ABC, the homogeneous coordinates for the line ABC, and you'll see that there's a non-trivial relation here, which is to be expected. So we were supposed to have these rather strange 2-dimensional subspaces in A2 times A2 mapping to a single line. So our lines are now parameterized by P2 minus a point. So we should have a map from A2 times A2 minus the diagonal onto P2 minus a point. And this describes the original construction that we're trying to do by describing a line by a pair of points. Let's move on to a 3-dimensional ambient space. Let's say A3, the affine 3 space. Now we can try to play the same trick. Of course, a pair of points define a line. Before we benefited from the other approach of trying to cut down a line by linear equations. Now if you do this, once again, you will have linear equations, this time of the form ax plus by plus cw plus d equals 0. So that would be one linear equation, but a single linear equation cuts down a plane inside of A3, not a line. So we need at least, well, in fact, exactly 2 of these. That means if I'm again keeping track of these coefficients of a linear equation, I really have a point in the projective 3 space, but I need 2 points in the projective 3 space. In fact, there's something about changing the planes. I can move the planes containing a line. So if there's a line and a plane, I can rotate this plane. In fact, the corresponding construction in P3 will be that if you have two planes, their coordinates defining points in P3, I can consider the line spanned by these 2 points. That gives me a whole family of coordinates, which correspond to a whole family of planes in A3. And well, sort of their common vanishing locus is the line that I started with. But then you see the problem that I started out with a line in A3, which of course gives a line in P3. Dually, the vanishing linear equations again gave me a linear space, a line inside of P3. So that the previous duality that worked in when we were discussing lines inside of A2, there a line gave me a point in P2. Here gives me a line again. So we cannot reap the benefits of this duality. But discussing these two elementary constructions had the following benefit. In both cases, it was somewhat clear that projective spaces appear very naturally. And now we should, in fact, just accept that the best way to think about this problem is to start with a projective ambient space. Of course, we can go back and forth. And now let's start building up the theory with some hindsight. So there's a notational thing to clarify here. I mentioned that AN, the affine n space, was kind of like a machine that associated to a field the vector space of dimension n over this field. But in fact, there is one more thing associated to an affine space, at least a way of thinking about it, is that whereas a vector space has its origin, and its origin is an important part of the information in that you're really considering the linear structure with respect to this origin. With respect to the affine space, we do not distinguish the origin as the center of anything. When we do have coordinates, yes, the origin is the center of our coordinates, but we can choose any other point to be our origin. In other words, the space of symmetries of the affine space include translations. Okay, so with this in mind, we can define a linear subspace like this. We take any subspace in the affine space, AN, let's say W, and then we say that if we were to translate coordinates so that a point on the space W becomes the origin, then W becomes vector subspace. So it's additively closed and closed under scaling. Another way to say it is that if you choose a point on W and then, well, you subtract this point from all other points in W, so you have had translation now, you get a subvector space of the affine space. So something that passes through the origin, obviously. When you're discussing the lines or surfaces in middle school, then this is not the definition that's given because you don't know the definition of a vector space. But this definition is very convenient, and I suggest that if this feels unintuitive to you, that you stop the video now and think about what was your original intuition and how it matches the definition that was just made. Especially for lines and free space, that's a very good practice to do. For the projective spaces, here's what we are going to do. We first realize that the projective space is the quotient of an affine n+1 dimensional space. Let's call it V. Inside of V, I'm going to take a subvector space W. So W must pass through the origin. And I can associate the projective space of W. Remember, the projective space sees the space of one-dimensional subvector spaces. So a one-dimensional subvector space of W is a one-dimensional subvector space of V. So there's a natural inclusion of P of W to P of V. And any subspace of PV, which might be Pn, if V is just the affine n+1 space. So for any subspace of PV, we will call it a linear subspace if it's the projectivization of a subvector space of V. Another part of the general notation is that a linear space will be called an M-plane if its dimension is M. And if M is 1, we call it a line. If M is 2, we call it a plane, and so on. A very useful exercise to do at this point would be to take an affine space AN, inject it into a coordinate patch of Pn, and then for any M-plane inside of the affine space AN, take its projective closure in Pn, and show that this also is an M-plane. This is now a projective M-plane. And you can do the converse. So the converse argument says that if you start with an M-plane in Pn and you restrict it to an affine patch, then you will either get an M-plane in this affine chart, of course an affine M-plane, or you will get the empty set. Here's what you can do. So remember, the inclusion of an into Pn work like this. You take an, you take a point in an, let's say this has n coordinates. You put a 1 before the first coordinate, so you now have n plus 1 coordinates starting with 1. Therefore, you get a point in an plus 1. In other words, we're viewing our an as a sort of an affine linear space in an plus 1, passing through this point 1, 0, 0, 0. And if you take a linear space in the original an, you're going to get something 1 times this linear space in an plus 1. What you now do is take the span with the origin in an plus 1 of what you just have. This gives you a vector subspace of an plus 1. In other words, linear subspaces in an gives you vector spaces in an plus 1 with this construction. And then when you pass to the projectivization, you get a linear subspace in Pn. And this is the projective closure. You can represent the projective closure like this, and this is, you can check. Grassmannians will be defined as the space parametrizing linear subspaces of the projective space. And through this passage to the affine charts, of course, an open subset of the Grassmannian we will see will parameterize linear spaces of the affine space. Let's go back to the space of lines in a plane. This time I want to study the lines inside of a projective plane. And now what happens is that the duality from before works perfectly, so that I will describe a line, and I can always describe a line, as the zero set of a homogeneous linear equation in the homogeneous coordinates of, let's say, x, y, z of P2. So a line I can write down as ax plus by plus cz equals 0, where a, b, c are constants, and this constant triplet is defined up to scaling, defined uniquely from my line up to scaling. And now the duality is perfect because any point in P2, including the one at infinity, so 0, 0, 1, will give me a line inside of the original P2. There's a side remark that we can do here, so that the equation ax plus by plus cz equals 0 is symmetric with respect to the roles that a, b, c and x, y, z play. In fact, x, y, z come from a projective plane, a, b, c come from a projective plane, and the equation is symmetric with respect to flipping these two around. And this is a standard example of duality, a duality between linear equations and subspaces of codimension 1. Let's study this linear equation a little bit more. Let's denote the space of lines in P2 by P2 hat. So we just saw that P2 hat is isomorphic to P2. I will denote its coordinates by A, B, C, and I will denote the coordinates of the original P2 by X, Y, Z. Now, what you can do is form the product P2 times P2 hat. In this product, you can form the zero set of AX plus PY plus CZ equals to 0. So this is well defined in this product. The zero locus will be well defined. And what happens is that you have two projections, one to the original P2 and one to the other P2 hat. So a fiber of a point ABC in P2 hat upstairs will then project to a line in the original P2. But you can do the converse. If you start with a point XYZ, let's say, its fiber upstairs will of course project down to a line. By duality, you can see that this must happen. And this just means that there's a line, one family of lines, so the ABCs, that pass through a point. That's of course clear once you think about it. There's a family of lines passing through a point, and this then duality has these two interpretations. Of course, another way of looking at it is that points on the original P2 correspond to linear equations or coordinates on P2 hat. Here's how you can generalize this construction. Start with Pn and consider codimension 1 linear subspaces. Codimension 1 means dimension n-1, and essentially by definition you can see that any codimension 1 linear subspace will be the zero locus of a linear equation, and the coefficients of this linear equation will then give you a point on a dual Pn. And here you can now also construct this product from Pn times Pn hat, let's say this dual space, parametrizing linear equations on Pn. And you will see once again that there's a duality, that a point on the original Pn defines a codimension 1 space of subspaces, and conversely, of course, point on the dual Pn defines a linear equation, which then defines a codimension 1 subspace. This is the first example of a Grassmannian where we could parameterize codimension 1 subspaces of a projective space by its dual projective space of the same dimension. You could actually make this even simpler. You could have considered the space of points on Pn. Obviously, Pn parameterizes the space of points, but there is something fitting into our definition. A point is, after all, a linear subspace. It's the projectivization of a one-dimensional subspace. Therefore, even points on Pn was an example of a Grassmannian. In this case, the space of points of Pn is Pn itself. We saw the space of codimension 1 objects is Pn, or dual to Pn. And the more general case we will do in the next part.